So today we are going to do significance test for means with one sample. So it's just one sample will be taken and we are going to test a claimed value. So yes, we are transitioning from confidence intervals back to our hypothesis testing. And so our first question here says, what is the test statistic T? So the T-star critical value, which we use for confidence intervals, that's how far we need to go out to capture the middle. But the test statistic T is just slightly different, but it is also kind of a standardized distance. So the T-test statistic for means is just like the Z-test statistic was for proportions. And I know you're going, I don't remember what that was. So I'm going to remind you. The test statistic, T, it tells how far in standard units the sample mean, which is X bar, is from the claimed mean. And that claimed mean is going to have a notation of mu sub 0 or mu naught. Either way, however you say that, that would be the claimed value. Kind of like we had with proportions, we had that P naught or that P0. This is the claimed mean, is mu 0 or mu naught. And so basically, here's how it looks on the picture. In the middle, you have your claimed value, mu naught. And then you go out and you take your sample. Well, let's say our sample was above the claimed value. So there's your X bar. Then whatever that distance is in standardized units, that would be the T-test statistics value. Now, this situation that I've drawn on the board is in the event that our sample mean is above the claimed value. Could it be that our sample data is below the claimed value? Sure. And if that happens, what would the T-test statistic be? A negative number, okay? So it can go in either direction, all right? Now, there's also something else that the T-test statistic does that's super important. It cuts off a very special area. So the area that is as extreme or more extreme than the T-test statistic is known as, anybody know? What is the area that is as extreme or more extreme than the sample T that we got? Is it ringing a very faint bell, maybe? As extreme or more extreme, that's the p-value. The area that is as extreme or more extreme than the sample that we got, the area that is cut off by that T-test statistic, that is the p-value. All right, so we can actually find that p-value, and we'll do that at the very end. So the T-test statistic is the boundary for the p-value. Okay, so before we continue, can somebody remind me, why in the heck am I using this T stuff? Why am I not using my Z distribution that I know and love so much?
Because it changes for means.
Because it changes for means, and why does it change for means? Because of the variability. Very good. So it is because, now here's the short answer. It is because we do not know sigma, which is the population standard deviation. That's the short answer. It's because we don't know sigma. Therefore, we have two variables And those are x bar and s sub x. So because of the fact that we don't know sigma, and we're having to go to a second level of variability, s sub x, that's why we use the t-test statistic, because it has more variability in it. If I know the population standard deviation for some reason, which I wouldn't, but if I did, if I knew the population standard deviation and I'm just estimating x bar, then I could use z for means, but I don't know the population standard deviation. If I did, I would know the mean, by the way, because the mean is part of the standard deviation formula. So, all right, cool. So the short answer is because we don't know sigma. If I knew sigma, I could use z for means. But because of the fact that we don't know sigma, we have two levels of variability. That's why we're using t. All right, cool. So, calculator. You guys got your calculators out? All right, everybody go to stat test. This is where our new test is going to be. We are doing a one sample t-test for means. If you go to stat test, now this one's kind of interesting because it's just it's very short in the calculator what you're going to use, or what the name of it is. It's number 2, which is just called a t-test. It's number 2. It's called a t-test. If you guys want to go ahead and go there, then you can see what the inputs are that you're going to need to put in. It looks kind of similar to the confidence interval one. You have a couple of options. First of all, you need to tell your calculator, do you have data or do you have stats? Again, just like with confidence intervals, if you have the individual data from the sample, you would go to data, and it's going to require you to have the data in L1. If you have summary of all the data in the problem, then you're going to use stats. All right, so look at data. We're going to look at data first. The first question it's asking you about is mu naught. And what did I tell you just a few minutes ago that mu naught is?
Claimed mean.
That's the claimed mean, and that's going to be in your hypothesis. This is your claimed mean. All right, now if you have data, again, it's going to say, hey, where's your list? Hopefully you have it already in L1. If you don't, you'd have to go back to L1 and do that. Your frequency, you're always just going to leave it at 1. All right, and then the next thing should look kind of familiar as well. We saw this with proportions. It is, how is the true mean mu related to this claimed value? Is it not equal to, less than, or greater than? So you basically, what's the sign of the alternative hypothesis? And then it asks you whether you want to calculate or draw, and you can do either one. I don't care, it doesn't matter. And you'll get the t-test statistic and the p-value is what you'll get. Make sense? Beautiful. Everybody go over, hit the right arrow to stats, and hit enter so that it'll change the inputs. And you can see what we're going to need there. Again, we're going to need mu naught, which, what is mu naught? That's the claimed mean. That's your claimed mean. All right, and then it says, hey, what's x bar? Because you just told me that you have the summary of the data, so tell me what x bar is. That is your sample mean. That would be given to you in the problem. S sub x, that's your sample standard deviation. And that's your sample size. All right, and then again, you need to tell your calculator what is your alternative hypothesis that you're trying to get evidence for, and then you do calculator mean or draw and blah blah blah. Again, your calculator is going to tell you what the t-test statistic is, what is the p-value, and then you're going to be able to make your decision, and life is good, and it's so fun, right? Yay! You guys have any questions about anything that the calculator is showing you there? No? Everybody's happy? Okay. All right, so that little picture at the bottom, it's just showing you basically your alternative hypothesis. If your alternative hypothesis says that the true mean is greater than the claimed value, you're looking for evidence on the upper end. If your alternative says that the true mean is less than the claimed value, you're looking for evidence on the lower end. And if you say that it's not equal to the claimed value, then you're looking for evidence on either side. You don't care which one it comes from. Cool? Let's do a problem. Woohoo! So on your green reference sheet that I gave you today, on the front side is the one mean t-test, which is what we're doing right now. And on the back side is the two mean t-test, which we will do on Friday and Monday. The two one there's two different options, so that it's going to take us 2 days. So we're going to do that on Friday and Monday. All right? So if you guys want to follow along on your green sheet, feel free. Here we go. A machine is supposed to fill bags with an average of 19.2 ounces of candy. The manager of the candy factory wants to be sure that the machine does not consistently underfill or overfill the bags. The manager takes a random sample of 75 bags of candy produced that day and weighs each bag. The sample mean weight was 19.28 ounces and the sample standard deviation was 0.81 ounces. Conduct a significance test at the alpha equals 0.1 significance level. What are we going to do? State, plan, do, conclude. Yay! State. All right, what are we going to do?
Test.
We will test. All right, so we're not estimating because estimating is what we do with confidence intervals. We will test. We will test at alpha equals, what does alpha equal? 0.1. It says so in the problem. That's the only reason we're using that one. Our null hypothesis would be that mu equals, we're doing a mean problem, so we're using mu. Mu equals, now what is the machine supposed to be doing? 19.2 ounces. That is what the machine claims it's doing. And the alternative hypothesis, what we're trying to check out. What is the manager trying to make sure that the machine is not doing?
Underfilling or over.
Under or over. So what is our alternative hypothesis? Mu does not equal 19.2 ounces. Perfect. Because I used a mu, I need to define it. So mu equals the true mean amount, I guess. Yeah, the true mean amount of candy in bags. All right, cool. Did that feel kind of familiar-ish? Okay, I hope so. The only difference here really was that we used mu's instead of p's. Everything else was pretty similar. All right, plan. Random. Do we have a random sample? I have an SRS of 75 bags. Woohoo! 10%. 10 times 75, that's 750. Do you think that 750 is less than the population of bags produced? I mean, let's think about it, guys. It's a candy machine. You think this candy machine's producing more than 750 bags? I would hope so. Otherwise, we're probably not getting a bang for our buck. So there you go. All right, random 10%, and then the normal. This is the one that changes because we're doing means, not proportions. So there's no NP, none of that mess. So, first question. Is the population normal? Did it tell us in the problem that the population was normal? No. It did not, so we can't use that one. Second option. Is the sample size bigger than 30? Ah, yay! So n equals 75, which is greater than or equal to 30. So the CLT applies. Bonus question. What does the CLT stand for? Central limit theorem. You got it. So central limit theorem applies. Okay, I have a question for you guys. If our sample size had been less than 30, what would we have to do? A box plot. But would we have been able to do a box plot with the information we've been given? We would not have. So I'm just going to give you guys a heads up. if you get data given to you in the problem, like the list of the data, chances are you're going to have to go to the box plot when you get there. Okay? That's just kind of a, oh, dang, here we go. We got to make a box plot. All right, cool. State plan. Any questions?
Are they having a dance party?
Probably. Okay, cool. Let's do the do then. Let's do. Yeah, I don't know what's going on.
Oh, are they practicing?
Oh, mate. Well, no, because, well. All right, do. We're going to use a one mean t-test. We're going to use a one mean t-test. That's a mean old t-test we're using. Sorry, I can't help make that joke every single time. All right, so we're going to go to our calculator, stat test 2. It's a t-test, stat test 2. Do you have data or do you have stats? You have stats. All right, cool. First question, what is mu naught? What is the claimed mean? 19.2. Second question, what is x bar? What was the sample mean? 19.28. S sub x, what is the sample standard deviation? 0.81. N, what was the sample size? 75. And what is our alternative hypothesis? Mu does not equal the claimed value. Perfect. You should get the t-test statistic, and the next thing underneath the t-test statistic is what? That's the p-value. Don't be lured into thinking that that's somehow a proportion. That is not a proportion. That is the p-value. Again, I hate that it doesn't say that for you, but it is the p-value. Okay. I'll let you guys catch up here for a second. Plug in your data. Well, your stats, I guess. Plug in your stats. And then get your t-test statistic and your p-value. All right, what is your t-test statistic? 0.855. What is your p-value? 0.39. Okay, cool. What does this mean? This means that our particular sample was less than 1 standard unit away from the claimed value, and the probability of getting a value that extreme or more extreme just by chance, just by some random sampling variability, is 0.39. All right? So, conclude. Okay, we are 95% No, you don't do that. I hope you didn't write that. We are talking about the p-value, which is 0.39. How is that related to the alpha?
It's greater than.
That is greater than the alpha value of 0.1. And when the p-value is not lower than the alpha, what do?
Fail to reject.
We fail to reject the null hypothesis. We are failing to reject the null hypothesis. And if I'm not rejecting the null hypothesis, do I have convincing evidence for the alternative?
There is not.
There is not convincing evidence. That the true mean is not 19.2 ounces. We do not have convincing evidence that the true mean is different than 19.2 ounces. So is the machine working properly?
Yes.
Yes, it is. It is not over or under filling. It seems to be doing its job just fine. That wasn't so bad, was it? I mean, other than writing a lot. Okay, what type of error could we have made? Why is it a type 2 error, folks? Because we failed to reject the null hypothesis, we could have made a type 2 error. What does that mean in context of this problem?
The machine could be not working properly.
Good. So we said machine works properly, but it does not. And I guess I should have written this. You can add it if you want, if you need to. This is just type 2 error since we failed to reject the null. So if you need that, that's why we made the type 2 error. It's because we failed to reject. And that would be us saying that the machine works properly, but it does not. It would be a terrible error to make. All right. How'd that feel? I mean, other than your hand is cramping and all that fun stuff, that was hopefully not too tough, not too difficult at all, right? Right? Feeling kind of familiar, I hope, ish. All right. Ready to move on? Let's do it. Okie dokie. How do we make decisions based on confidence intervals? All right. If the claimed value, the claimed mean, that's our mu naught. If the claimed value is in the interval, think about that for a second. The claimed value is within the interval of possible true values. Would you want to reject or fail to reject the claimed value? I would fail to reject. Good. We fail to reject the null hypothesis of the claimed value. So it should hopefully make sense that if the claimed mean is not in the interval, we reject the null hypothesis. If the claimed value is not in the interval of possible values, we should reject that value. Now, one thing I do need to make sure that we remember is that confidence intervals are only related when the alternative hypothesis is a not equal to. That's the only time that the confidence interval is related to the hypothesis test. Okay, so with this information in mind, you guys should be able to do the next two examples pretty easily. As long as you remember how the confidence level is related to the alpha. So if your confidence level is 95%, what's your alpha value? 0.05, 5%. And if your confidence level is 90%, what's your alpha value? 10% or 0.1. Okay, you guys should be able to answer the next two questions fairly easily. I'll give you about a minute, maybe two, just so you can read it. Next two questions on your paper, these multiple choice questions. You got this. Easy peasy lemon squeezy. Once you have your answer, check with your neighbor, see if they got the answer. Okay, first one. We want to test that the mean is 4.06 against the alternative that the mean is not 4.06. A 95% confidence interval for mu is calculated, and we get 3.98 to 4.06. Based on this, what decision would we make? All right, are we going to reject or fail to reject 4.06? We should fail to reject it because 4.06 is in the interval. So we can fail to reject the null hypothesis. Oops. Okay, now, because we had a 95% confidence interval, what's the alpha value? 0.05, so what's the answer? D. Cool? All right. Mu is 180 against mu does not equal 180. Our confidence interval is 169 to 178. What should we do? We're rejecting that 180, so we're going to get rid of those. And 90% alpha equals 0.1. So what's the answer? A. Easy, right? Do you guys want your test to be full of those kind of questions?
Yeah.
Wouldn't that be great? Just 10 of those. Man. How about at least one? All right, we'll go with that. We'll go with one. All right, we're going to kind of do something a little different. So this says that we are testing a null hypothesis that the mean is 10 feet against the alternative that the mean is less than 10 feet based on a simple random sample of 20 observations from a normal population. The t-test statistic is t equals negative 2.25. What is the p-value? So, here's what we have. We have a distribution where we have a claim that we have 10 feet in the middle. That's our claim. We are looking for evidence below that mean, and we find evidence 2.25 standard units below the claimed value. This is where our sample was at. Our sample was 2.25 standard units below the claimed value. And I want the p-value. So really all I need is the area that is as extreme or more extreme than this particular area or this particular sample. So I just need that area. Any ideas how I get an area of a distribution? How do I find the area of a distribution? Normal CDF, right? Yeah. But wait, time out. This is a T distribution, not a normal Z distribution, which in my calculator, when I say normal CDF, it's a Z distribution. This is a T distribution, which is a normal type of distribution, but it's not the normal distribution. It is a T distribution. So do me a favor. Go to where you would normally get normal CDF and see if you see something that could help us find an area for a T distribution. What? There's a T CDF? No way. Are you serious? That's crazy sauce.
Crazy sauce.
Okay, so yeah, guys, just like we could do this on a normal Z distribution, we can do this with a T distribution as well. It's TCDF. What option number is that for you guys? 6. Okay, so second vars, go down to TCDF. So it's asking you for the lower boundary of this region that is shaded. What is the lower boundary? Negative infinity, so that's negative 1e99. What's the upper boundary? Negative 2.25. And then it asks you a very different question. It does not ask you for the mean and the standard deviation because it could change, right? This time it's 10 feet. Next time it could be 87 feet. I don't know. So what it does ask you is DF. What does DF stand for? Degrees of freedom. How do you get degrees of freedom? N minus 1. So what are your degrees of freedom for this problem? 19. And when you hit enter, you will have the p-value. the area that is as extreme or more extreme than this particular sample. And what did you get? 0.018. There's your p-value. Now you could make your decision based on whatever the alpha level might have been. One caution that I would like to give to you is if you do a problem like this, and let's say this had said not equal to 10, that means you could get your evidence from either side. But of course, guys, when you're taking one sample, you're only going to get evidence from one side. So I might still get the evidence right here. But if that had said not equal to, I would have just as easily had taken evidence from the complementary side, where 2.25 and higher. So what would I do to get the true p-value if it's a not equal to double-sided test? I would multiply that by 2. Okay? So if the alternative is not equal to, you should multiply the p-value by 2. You got to double it. That's just if you have a not equal to. Cool? Cool. All right, you guys. Almost done. Again, this is review. Let's see if you remember it. A researcher plans to conduct a significance test at the alpha equals 0.01 significance level. She designs her study to have a power of 0.9 at a particular alternative value of the parameter of interest. The probability that the researcher will commit a type 2 error for the particular alternative value of the parameter is what? We are trying to find the probability that she commits a type 2 error. Anybody remember how to find that? Huh? That's beta. Okay, cool. So we remember that this is beta. That's awesome. Nice. And how do I get beta? Yeah, beta and power are complementary, and so beta equals 1 minus the power. Beta equals 1 minus the power. And so what is this equal to? 1 minus 0.9, which is 0.1. Dun da da da. Okay, plot twist.
Is there a Hannah Carpenter?
Oh my gosh.
Yes.
She left her bed and all that. Or she did.
All right. Just out of curiosity, does anybody know for this problem what the probability of a type 1 error would be? That was very sketch. Does anyone know what the probability of a type 1 error would be in this problem? 0.01. How did you get that? You guys, don't forget, the alpha value is literally the probability of a type 1 error. Okay. Last question. This is also review. How could the researcher increase the power of her test? She could increase her alpha, or she could increase her sample size. You got it. You remembered a lot today. All right, you guys, how was it? I understand. But not terribly hard, right? Okay, let's hope not.